So, summarizing, we have, well, this is what we wanted to compute. And that is something we could write like this. Plus EA wedge EB, EA gamma D BC ED, minus 1/2 EA wedge EB, A ABD, gamma DCE EE. So the first thing we computed was this, and we could show that this is equal to d omega dc ed minus gamma dbc d eb ed. Then what we showed was that this object here was equal to d e d. So now we collected everything and we see what we get for the right hand side. So the right hand side is omega ed wedge omega dc e e. Okay, plus. Second, we replace with its result d omega dc e d. Then we have minus gamma dbc d e b e d. And the last part is plus because we replaced this entire thing. D E D gamma DC E E E. Now we have to confirm that these two cancel, which is true. And then we write things so as to factor something, ed. So let me write d omega dc plus omega, I want a d there. C remains where it is. The d is this one, and then you have a contraction of indices in the middle, which makes it useful to use this matrix notation because, yeah. So this we define, this is a two-form and a vector, and this we define as RDC ED, where R is just the two-form, the coefficients, and that is the curvature. So R AB is the omega AB plus omega AC omega CB. And when we want to suppress the matrix indices, we will also write R equal d omega plus omega omega. and you have to understand where the indices are, and where they are contracted, and where the forms are. And as far as the torsion is concerned, torsion is the covariant derivative of E, which means dE plus omega E. So these are the basic quantities in the differential form notation. Curvature and torsion has two forms, both are two forms, but one has just one index and the other one has two. That's the only difference. Well, they are different objects. So it is interesting to work on the space denoted by lambda k m n, space of k forms that have m flat space indices up and n flat space indices down. So in flat space there are tensors mn, so let's see which spaces the basic objects we have defined so far belong to. So for example, EA. EA are differential forms, and they have one upper index. T, the torsion, they are two forms with one upper index. R, AB, is a two form with one index up and one index down. And so on. So let T, A1, AM, B1, Bn be a generic element of this space. We will see later how we transform the indices A and B, flat space indices, when we change charts, as we said. For the moment, we just work locally. We want to define the covariant derivative of this. And we will see that it has the right properties to be a covariant derivative. But for the moment, let's give the definition, nabla of T A1 AM B1 Bn equals the exterior derivative, that's a form, so whatever that is, plus something else. Contributions constructed with a spin connection. So if T has no indices, no flat space indices, the covariant derivative is just the exterior derivative. As far as space-time indices, we do not need connections for the exterior derivative when we use differential forms, as we recall. But instead, here there are these flat space indices, so let us write the sum explicitly. You have omega, AIC, T, A1. Here it means that you suppress the index AI and you replace it by C, and you do the same for everyone. Then there is another contribution, minus 1 to the power k, where k is the degree of the form. And then you have sum for I going from 1 to n, t, a1, am, b1, bi, you suppress it and replace it with c, and then you multiply by omega c pi. So for example, let us check it with the torsion. That is k equal 1. Well, there is only one upper index, so you have d plus omega correctly. EV. If let WA be a zero form with one upper index, VA be a zero form with one lower index. So in this case you can write the covariant derivatives. WA is the same as above. But for V there is a minus sign. Minus because k is equal to 0. So minus 1 to the k is minus. So you have minus t, your t, c, a. So in particular, if you want to compute the covariant derivative of this object, that should be equal to the exterior derivative, and this covariant derivative should obey the Leibniz rule. So should be, this is just a check, we should be able to write this, and then we copy. Omega EBW PVA plus WA DVA minus WA omega V B omega B A. So let's see. These two cancel, and so you get correctly what you expect. Okay. In general, This is an exercise. The del of t k, let's say its degree as a differential form is denoted by this index k. Wedge S H, let's say C1 CR D1 dP, that's equal to del Tk E1 AM B1 Bn wedge S H C1 CR D1 dP. And then since nabla has degree 1 and this has degree k, when you cross you have a coefficient that is -1 to the k. Nabla S. dP. So now that we know what the covariant derivative is, let's see the Bianchi identities. In this language. So first we have T is this. These are matrices. Omega is a matrix. E is a vector actually, because E has one index. But the Bianchi identity is del. Let's compute del T. And let us recall that T is a TA, one index. So its covariant derivative is very similar to the covariant derivative of the feedback, because it has just one index. Now we replace this thing here. And so we find d dA plus omega A plus omega dA plus omega A. DDA is 0, because d squared is 0. Then you have d omega E, and here we can apply what is the exterior derivative of the wedge. So you have a Leibniz rule like this, plus, since d is a fermion, because it's a one form, 1 degree, and omega also, you have a minus sign. So here you have a minus sign omega d plus omega dE plus omega omega E. So these two objects disappear, and then you collect E, and you see that what you factorize is the curvature d omega plus omega omega. So the first Bianchi identity is this. The covariant derivative of the torsion is R wedge E. Last time we wrote it in a different way. Let's recall it. It was R x y z plus cyclic permutations equals del x t y z plus same. So this is the covariant derivative of t equal to r on the basis. It's exactly the same thing. When the torsion is 0, you have this equals 0. So let's see what that is. So t equals 0 means that the Bianchi identity is this. Let's write it explicitly. R A B E B equal 0. Now RAB is a two-form. Since RAB is a two-form, it can be expanded in a basis of two forms. And so I can define coefficients that expand this, not in the base dx nu, because we don't want the space-time indices, but we could. We expand it that way, and the coefficients then are the Riemann tensor. So you have 0 equals RAB EB, that's 1/2 R CD AB EC ED EB. So this is a three-form and it must be 0, which means that if you completely antisymmetrize these three indices, you must get 0. And that is what you know as the first Bianchi identity. No need to antisymmetrize in the first two, so you just have the sum of the cyclic permutations of the three indices. This is a property of the Riemann tensor that follows from vanishing torsion. And that is the usual identity that you know about. We will also write this object as R, A, B, C, D. Because in physics language, that's how we order them. More frequently we will use this. The other Bianchi identity instead is more powerful than the one we wrote before, because we will see that it doesn't need any assumption and it's simpler than before. So let us start again from R, which is this. Bianchi identity is second Bianchi identity del R equals 0. Here we have to understand what del means, because we have one up index, and for that we have to use the usual notation. But then we go back and check what we do with the lower index. Here, this is the covariant derivative. So you have an omega to the right and minus 1 to the power k, where k is the degree of the form. And since the degree of the form is 2, we just have a minus there. So minus R AC omega CB. Okay, so in understanding the indices, this can be written as dr plus omega r minus r omega, because the indices to the left are always A and the indices to the right are always B. Now we replace this inside, and what do we get? D of R plus omega R minus R omega. And what is that? So again, d omega is 0. So you have d of omega wedge omega, and that will be d of the first omega wedge omega minus, because this is a one form, this is an exterior differential, exterior derivative, minus that. And then the rest you just copy and you see where we go, because as simple as that. Now if you did the exercise, you will have found that it was not that simple. In the vector field approach. Now we discuss how we change basis charts in the flat space indices. That is a change of basis, which we define on the forms EA, like that. Omega can depend on the point. And well, if this is the change on the differential forms, the change on the vectors is omega minus 1 B A E B. Indeed, we want EA EB equal delta EB, but we also want EA prime EB prime equal delta EB. And that is correct because EA prime is omega AC EC form acting on omega minus 1 B D E D. So when this is a differential, this is a vector, differential of a function times a vector, the function goes out. Then you have EC ED, which is a delta of C and D. So this is delta AB. Omega, for the moment, can be any function of the linear group with real values. Has to be invertible because we want that to be a basis, but it doesn't need to be a Lorentz transformation. We will see later when we will have to restrict to transformations of the Lorentz group. For the moment, can be any invertible matrix. And why that? Because we are studying a generic change of basis. If you have a basis of vectors and you multiply it by a generic linear transformation, you will have also a basis. It doesn't need to be orthonormalized or anything. Let's see how objects transform. So the basic differential forms and vectors transform as we have said here. Then we can check how the torsion transforms and how the curvature transforms. But to derive how they transform, we have to work a little bit and check how omega transforms. So that's what we have to do now. So let's start from the definition. And we want, after the transformation, to call these A, B, C prime EC prime. We want this. Okay, so these are vectors. Vectors transform as we said before. We replace. That's del omega minus 1 A D ED. Here we have omega minus 1 B E EE. And now we have to apply the properties of del. Here, when you have a function times a vector, the function goes out. Here, instead, you have to apply the Leibniz rule. So the first goes out. And for the moment, let me copy the rest. Now we apply the so-called Leibniz rule here, so you will have two contributions. One will be this one, plus you have to act by means of the vector on this function. Whatever it gives. Okay. Now the first object here can be written as gamma. Gamma DEF EF. And the second object, let me write this EF. This is a vector. EF, you see, is omega minus 1 of E prime, because I want to isolate an E prime to the right. So instead of writing EF here, what can I do? Omega F G, yes, G, EF EG prime. So here I will be able to read omega prime, gamma prime will be equal to this, which is what you expect by transforming every index with a matrix omega, plus a rest, because it's a connection, it's not a tensor, as you might remember. Here we just copy this thing that I forgot, omega minus dA here. Omega minus 1 dA. So we copy that, omega minus 1 dA ED omega minus 1 EB, and then we do the same for this So apart from changing names to the indices, we can factorize these objects and read the transformation of gamma. So gamma A, B, G prime is equal to omega minus 1 dA omega minus 1 EB gamma dA DEF omega GF plus omega minus 1 dA ED omega minus 1 EB omega GE. Okay. So we can now, it's better to write the transformation of this, which is gamma A, B, C, EC prime prime. The prime of that we have, and then we have to work out the rest. Let us can simplify something, because as you see we are contracting this index with an E prime, but an E prime brings an omega that cancels this omega minus 1. And we have the omega minus 1 both here and here. So that's a simplification. So let's do things right here. Now A becomes the index G, and B remains B. So you have omega minus 1 something B gamma D. D is what becomes A. E is this thing, F omega F A times G is A, yes. Omega, no, I don't understand this A here. Okay. Oh, yes, this one. DEF EB. Yes, we have to. A is not contracted. A is something. Let's see. C is free because we have this form. Easy. Plus, this disappears, so you have E, again the form C, omega minus 1, EB, omega G, G is E, A, E, E, C. So, omega minus 1, EB, D, EF, AF, plus ED, yes, yes. we have to leave it there, and we will continue on Monday.